So my name is Erik Grumstrup. I'm an assistant professor of material science and chemistry here at Montana State University in Bozeman. My group sort of operates at the intersection of chemistry and physics and material science. And so generally we're interested in materials properties, and in particular how those properties, those electronic properties of materials change as the material size shrinks down to the nanoscale. The really exciting thing about nanostructures is that we can have new properties that we couldn't have otherwise without shrinking these materials down to the very small scale. Now, the prerequisite for being able to use those properties ultimately in our technology is that we have to understand those properties at a very deep level. And so that's really where my group comes in. We try to develop this fundamental and detailed understanding correlated in very precise ways. When we make nanostructures, they are intrinsically heterogeneous. The size changes and the shape changes. The composition can even change. How the material behaves in the bulk versus near the surface changes a lot. We're one of a handful of groups in the US that couples ultra-fast spectroscopies, which uses very short laser pulses to be able to provide very high time resolution. So we couple these advanced spectroscopies with optical microscopy. And so the microscopy part of it gives us very high spatial resolution, which allows us to bring unprecedented insight into the fundamental physics of these interactions. The primary area that we're really interested in are understanding carrier-phonon interactions in perovskite nanostructures. That phonon-carrier coupling is really the single most important determiner of efficiency of the functional properties. So it determines how much heat is lost or how much energy is lost in a solar cell when it absorbs light. It determines how fast electrons move from point A to point B in a transistor. It determines the efficiency of the screen on your phone or on your computer. And so this fundamental property really has an important impact on all of our everyday lives. And so understanding those aspects is sort of one of the central points of this proposal. Current techniques are simply incapable of characterizing these sorts of interactions at this length scale. They don't have the sensitivity, and nor do they have really the spatial resolution to ultimately be able to disentangle the structure-function correlation that is so important to nanoscale optoelectronics and electronics. The initial goal of this project is really to develop this new instrument that will provide really unprecedented insight into the carrier-phonon interactions in these materials. The primary component is that we're going to do time-resolved, ultra-fast Raman spectroscopy on materials. So the idea here is that we can actually watch the evolution of material vibrations with 50 to 70 femtosecond time resolution. We're going to couple those spectroscopies to an optical microscope, which again will bring us this very high spatial resolution and ultimately be able to have the sensitivity to study individual nanostructures. So we hope to achieve a factor of about 1 million improvement in sensitivity, so we can really, peel back all the heterogeneity and increase the precision with which we're able to ask questions. With the very high spatial resolution, we can take a step back from all that and say, okay, what's happening at the individual structural level? And then we can make very precise correlations between particular structural variables and the functionality that we see based on our spectroscopic observables. So this work, and really my entire career in some sense, has followed this parallel to spectroscopy over the past 50 years. So I started doing gas phase spectroscopy. Then as a graduate student, I did liquid phase spectroscopy of molecules and trying to understand their dynamics. And now at MSU, my group is really excited about trying to understand fundamental chemistry, photochemistry, and physics in solid state materials. And so what's really exciting to me about that is to be able to do the fundamental science I love and be able to ultimately see these results manifest in the technologies that we all enjoy every day.